Hi guys, Mrs. H here. We're going to go ahead and take a look at graphing along with that CER strategy today. So what do graphs do? They tell you what the data says. So graph would be the evidence in that CER, so it's the E. It tells you if there's a difference in the data set, it uses statistical formulas, and it provides facts. And so we have several different kinds of graphs. So you're familiar with a pie graph. Remember, pie graphs show the evidence in percentages. They provide ranges within each data set. And they also show us high points and low points. So again, we're looking at percentages. Sometimes we see pie graphs even part to whole. So we have a whole would be 100%. So but part of that whole would be a category. So we see categories in pie graphs as well. A bar graph is actually categorical data, and we're comparing the categories. It's not part to whole. So all of these things aren't necessarily in the whole, but we're comparing categories. This is often misused because we want to remember you have to be able to put a data set into a category. So the evidence that you would be providing are comparing categories. So for example, Sunday. You can't have half a Sunday. You can't have half a Monday. The day is either Sunday or the day is either Monday. You can't have anything in between. So that's our bar graph. And then a line graph. Line graph usually shows trends in data. Again, you're going to have on a line graph, your data is no longer categorical. You know, you can keep splitting the data in half. So you could have 1, you could have 1.5, you could have 1 1/4. So we can split up the data into, it's no longer a category. A lot of times we see it over time. It does not have to be over time, but anything that is numeric in value, typically it is time, but it does not have to be time. It could be speed, which is again numeric. It could be weight, which is again numeric. So again, our evidence is going to be a data that is numeric and it's showing a trend. Now, a scatter plot is different than a line graph. Scatter plots, you're not going to necessarily connect the dots. This one, I would argue could be a little tricky because it does look like you could connect the dots, but we want to see a relationship in our data. So a relationship between two variables. The variables, again, will be numeric in value, but then the data doesn't necessarily have to be connected up, and often it's not. So maybe you have several data points for one value, like on this graph, the effect of food, so the amount of food. If you look at 5, there's actually 2 variables there. I know it's kind of hard to see, but there's actually 2 variables. One is slightly off. If you look at 10, it occurs again at 10. So the variables, again, there are 2 variables for each one of those. They're not exactly the same. And so this results in a scatter plot. Sometimes we see in scatter plots there might be an outlier. We'll also have, hold on one second. So scatter plots will also have a y-intercept in their data set. So again, when we're looking at our evidence, the evidence is showing a relationship. And so this is a gray slide, so I'm going to go ahead and give you a minute to complete this one. You are going to be identifying each type of graph as either a bar graph, a line graph, a scatter plot, or a pie graph. So So we're going to continue on with scatter plots and that relationship. So scatter plots will show either a positive relationship or a negative relationship. So positive relationships show variables which are both increasing. So our x-axis and y-axis both increase, resulting in a positive relationship. If it's a negative relationship, one variable will increase while the other variable decreases, and we call this again a negative relationship. Now, within these relationships, we can show a strong relationship or we can show a moderate relationship. A moderate relationship, so imagine drawing a line through the dots and you ask yourself, how close are the data points to the dots? How close are the data sets to the line? If they're very close to that imaginary line that you draw through the data, then it is a strong relationship. However, the farther that those data sets move away from the line, the less it becomes moderate of a relationship. There is such a thing as no correlation. If we don't see a pattern in the data set, then there isn't a relationship. And so here are some examples of what I was referring to. So notice we drew that line. That relationship is represented as R. It's an R value. And so you can see that imaginary line. Notice the dots that are close have a strong relationship to that line. The dots or the data points that are farther away show a weaker relationship. And so on this one, I would like you to identify the type of relationship. Is it strong? Is it moderate? Is it weak? Is it a positive or negative? Or is there no relationship at all? And so in general, when analyzing graphs make the claim based on data. The data is the evidence. So we can make a claim about a graph and then use the data on the graph to support the claim. Good graphs have a good title. They have accurate and a consistent scale. All parts are labeled. If appropriate, they have a key, and the data is properly entered. And so we can see all of those things on the graph here. And so on these, we can see some of these do not have titles. Some of these, the data is not entered accurately. If you look at the 2012 presidential run, the percentage is over 100%, so the data is not accurate. There's such a thing as too much data, which we see in the pie graph. And then if you look at gun deaths in Florida, it's actually very misleading. It makes it look like there's a spike in 2005, when in fact, in 2005, there's fewer gun deaths in Florida. And so this is actually a reverse scale. And so it makes the data it's misleading. So again, these are all poor graphs because either there's no title, there's too much data, the data was entered inaccurately, or it's poorly represented. And so again, this is a gray slide. So on this one, I want you to delete the slides that are bad, and then with the graphs that are left, so the good graphs, please explain to me what makes them a good graph. And so now we can also look at graphs to do reasoning. So the reasoning goes beyond the data. So again, the data can make a claim, it can give us data, but then we have to go that next step. And what is the reasoning behind the data? What is the scientific analysis of the data? And so let's practice this. So here we have a gray slide. So we have student grades. So I want you to make a claim, provide evidence, and give reasoning. And so what claim can we make? Most students perform well in this class. Is it the best um, claim? No, but based on the data, it's pretty good. I would say it's adequate. Um, if the title was better, yes, we could make a better claim. Evidence. So, what evidence supports that most students are performing well in the class? 56% of the grades are a B or better, and 0% are failing. So, those are two evidences that are provided in the graph to support the claim that most students are performing well in the class. If no one's failing, I think that's pretty good. And if more than half have a B or better, that's really good as well. And so, what reason could we give for students performing well? Well, students are completing all their work, students are using their resources, and students are studying for tests. So, all of those would be reasons why students are performing well. So, again, notice how we can use the CER strategy to really understand a graph properly. And so, that's what we're going to be working on here in the next few days. So, if you have any questions, please make sure you're reaching out to me, and I will see you later. Bye.